You live in one of the emptiest neighborhoods in reality. When you look up at the night sky, you see a lot of stuff. Stars everywhere, the bright band of the Milky Way, maybe even some planets. Your brain says, this looks busy, this looks full. On human scales, that is true, but on the actual scale of the universe, the place you live in is closer to a near-perfect vacuum than anything your senses can handle. The shocking part is not that there is empty space between things. The shocking part is that the emptiness is the main thing, and the things are barely there at all. To get a feel for how extreme this is, take a simple chunk of space, say a cube 3 feet on each side, about the size of a big home appliance. Cosmologists estimate that on average, that entire cube of the universe holds about 1 proton, 1 basic building block of an atom, and usually not even that. The rest of that volume, all those cubic feet, are just vacuum. Now scale that up to a volume the size of a whole city in the United States, skyscrapers and suburbs included, and the basic statement stays the same. You are talking about essentially zero matter in that volume, maybe a few lonely particles drifting through after millions of years. Now compare that to the air in front of your face. In just 1 cubic inch of air, less than the space taken up by your thumb, there are roughly 10,000 billion molecules bouncing around. That is a number with 24 zeros after it, packed into less than an inch. You breathe that density in and out every second without thinking. Next to that, the universe as a whole is unbelievably thin. You, your body, your chair, your room are insanely dense compared to the cosmic average. You are not slightly denser, you are more than 99 point and then a ridiculous string of 9% denser than what normal looks like out there. You're the weird one, not the cube. So the obvious question is, why is the universe set up like this? So empty almost everywhere with just a few small pockets of high density. To answer that, you have to go all the way back to when the universe was young, a few 100,000 years after the Big Bang, when it was still a hot, glowing fog. We can still see the light from that era today as a faint microwave signal coming from every direction. It has a temperature of about 2.7 degrees above absolute zero, which is around minus 455 degrees Fahrenheit. This glow is called the cosmic microwave background, and it is basically a snapshot of the universe as a baby. When scientists map this microwave background across the whole sky with sensitive instruments, they color-code tiny differences in temperature, and what they see is almost boringly simple. The temperature barely changes from one spot to another, only by about 1 part in 100,000. Put that in plain terms. If one patch of sky is at 2.7000 degrees, another patch might be at 2.70003. Those tiny differences are not just about heat, they match tiny differences in density. Some regions had a tiny bit more matter, some had a tiny bit less. That is all the structure there was. Over billions of years, gravity takes those slight overdensities and gives them a boost. Where there is a bit more matter, gravity pulls a bit harder, more material falls in, the region gets denser, and the effect snowballs. Those tiny early bumps grow into clouds, clouds grow into galaxies, galaxies grow into clusters, and eventually stars and planets appear. Everything you see in the universe today, every galaxy photo you have ever looked at, started as a slightly denser region in that almost uniform fog. The important point is, the starting pattern was incredibly smooth, far smoother than your everyday intuition would expect. That leads straight into the disturbing part. Those early fluctuations could not be much smaller, and they could not be much larger, without completely changing the outcome. If the temperature and density bumps in the early universe had been weaker by even a factor of a few, gravity would not have had enough contrast to work with. The universe would have expanded, stayed smooth, and never formed stars or galaxies at all. You would get a thin, cold, featureless mist, and nothing like you could ever form. On the other hand, if those bumps had been much stronger, gravity would have pulled matter together too fast and too violently. You would make huge clumps, extreme objects, black holes and dense clusters, not stable spiral galaxies with long-lived stars in calm orbits. So you end up with a narrow sweet spot. The early universe needs to be almost perfectly smooth, but not exactly, just lumpy enough for gravity to draw out a thin web of structures and no more. That setting leads directly to a cosmos where most of the volume stays very empty, and only a small fraction condenses into galaxies, stars, and planets. The emptiness is not a mistake that happened later. It is baked into the starting conditions. It is the baseline. Structure is the rare add-on. This is where the picture flips in your head. The way we talk about space, we act like it is a big container with some empty space between things. That is a human scale view. On the real cosmic scale, it is the opposite. The emptiness is the rule, the things are the tiny exceptions. The cosmic microwave background is basically the universe telling you right from the beginning, I am going to be extremely smooth, extremely thin, and I will allow a small amount of structure on top of that, and that is all you get. You and everything around you are built out of those rare deviations from smoothness. So here is the hard message, put very plainly. The laws of physics do not seem to be tuned for a universe full of matter, full of life, full of observers. They are tuned for a universe that is overwhelmingly empty, with a small temporary network of galaxies where complexity can briefly show up. You and I live inside that network for a short time, and we are able to notice how strange that is. And that sets up the next, harsher question. If the default state of the universe is almost total nothing, and if all the bright, complex places are tiny exceptions built on fragile early bumps, what do the actual numbers say about how rare your specific situation is in all this dark, thin space? You hear that the universe has hundreds of billions of galaxies, and your brain says, okay, that sounds busy, that sounds like there should be life everywhere. So how can you possibly be rare in something that huge? The answer is, those big numbers hide how empty and spread out everything really is. Start with the observable universe. The part you can in principle see. Its diameter is about 93 billion light years. A light year is the distance light travels in a year, about 6 trillion miles. So 93 billion of those is a size your brain just cannot hold. Inside that volume there might be a few 100 billion galaxies. Sounds like a lot, until you think of each galaxy as a tiny dot floating in that gigantic sphere. The average distance between big galaxy clusters is tens or hundreds of millions of light years. That means if you flew past one cluster, you would travel for absurd amounts of time through almost nothing before you hit the next one. And even when you drop down to the scale of a single galaxy, the story does not suddenly become full. Take the Milky Way. It is about 100,000 light years across, a giant rotating disk of stars, gas, and dark matter. You see pictures of it, and it looks like a glowing pinwheel packed with light. But zoom into the actual distances between stars, and everything thins out fast. If the sun were a ping-pong ball sitting in New York City, the nearest star system, Alpha Centauri, would be another ping-pong ball all the way out near Los Angeles. Everything in between is not other stars stacked together, it is mostly empty space with a bit of thin gas and dust. So yes, the universe has big counts, big totals, big billions, but those are spread across a volume that is ridiculous. When you divide, what you get is not a busy universe. You get a few small islands, very far apart, inside a sea of basically nothing. That raises an obvious next question. If it looks so full in pictures, what does the actual budget of stuff in the universe look like when you do the full accounting? When cosmologists run the numbers, they find something that sounds like a bad joke. Only about 5% of the total energy content of the universe is ordinary matter, the atoms you are made of, the stuff that makes stars, planets, gas, dust, everything you can see with the telescope. Around 27% is dark matter, some invisible mass that does not shine or interact with light, but adds gravity. And the rest, about 68%, is dark energy, some kind of energy built into empty space itself that pushes the expansion of the universe to speed up. So if you think of the universe as a kind of cosmic budget, the part that can actually build chemistry, biology, and technology is the tiny 5% slice. The majority of the mass and energy is in forms that do not directly build complex structures you can live on. And even that 5% is mostly not in you. It is in hot gas between galaxies and stars and clouds and rocks, spread thinly through space. Zoom in on a galaxy cluster and you still find most of its volume is vacuum, with some plasma threaded through it, and the stars and planets are tiny specks inside that. So even in the best case regions, where the universe has put a bit more matter than average, you're still dealing with a lot of nothing, with a few particles scattered far apart. That leads to a sharper question. If galaxies and clusters are already mostly empty, what does that say about how sparse things are even in your local neighbourhood, around the Sun? Right where you are, in the part of the Milky Way where the Sun lives, astronomers estimate the average star density is about 0.004 stars per cubic light year. Put that into plain language. If you draw a cube of space that is 6 light years on each side, so 6 by 6 by 6, you get a block of volume that size, and, on average, there is less than 1 star in it. Most such cubes would contain 0 stars, just empty space and a very thin sprinkle of gas. Your closest stellar neighbour, the Alpha Centauri system, is about 4.3 light years away, around 25 trillion miles. If you drove a car at highway speed and never stopped, you would need tens of billions of years to reach it. But even at the speed of light, that is still more than 4 years of travel time just to get to the very next star. A good analogy here is a city at night where each streetlight is separated from the next by 25 trillion miles. That is the kind of crowded neighbourhood you live in. So your galaxy is huge, but its stars form a very thin mist spread over a gigantic volume. You tend to see pretty images of dense star fields because telescopes point where the stars are. But if you picked random points in the galaxy, most of them would land in mostly empty spaces. That brings you to the next tightening filter. Out of all those thinly scattered stars, how many can actually host planets like Earth, in regions of the galaxy that are not constantly getting smashed or sterilized? To get a planet like yours, you need a decent list of conditions all at once. You want a star that is stable over billions of years, not too massive and short-lived, not too small and violent with constant flares. You want a planet at just the right distance where liquid water can exist on the surface, not boiling away, not frozen solid. You want the right mix of heavier elements in the system, things like carbon, oxygen, iron, silicon, so you can build rocks, atmospheres, and complex chemistry. And you want to sit in a part of the galaxy that is not being blasted by frequent supernova explosions or torn up by gravitational chaos. When people talk about the galactic habitable zone, they mean the region in a galaxy where all those conditions are reasonably likely. In a spiral galaxy like the Milky Way, that is not the whole disk. The inner parts, close to the centre, can be too crowded, too hot, too full of radiation and violent events. The far outer regions can be too poor in heavy elements because fewer generations of stars have lived and died there, so there is less raw material for complex planets. The result is a kind of ring or band at certain distances from the centre that looks like better real estate for Earth-like life. So now look at what you have done. You started with the whole observable universe, already mostly empty. You picked out the tiny fraction that is in galaxies. Inside that, you checked out the small parts where stars are not too far apart and not too extreme. Inside that, you picked out the narrow band of stars with stable, long lives. Inside that, you pick the ones with planets in the right temperature zone with the right chemistry. Step by step, you have sliced away almost everything. You are not just somewhere out there in a vast, friendly cosmos. You are sitting inside a thin shell of stars, in a thin disk, in one mid-sized galaxy, inside a universe that is almost entirely empty and dominated by things that do not care about life at all. And that sets up the next, deeper question. If you want to know whether this was ever going to turn out any other way, you have to ask, did the universe's baby picture already lock this sparse, almost empty future in from the start? Right now, no matter where you point a sensitive microwave telescope in the sky, you see the same freezing glow. sitting there at about 2.7 degrees above absolute zero, around minus 455 degrees Fahrenheit. That glow is not from your galaxy, not from nearby stars. It is the leftover light from when the universe was only about 380,000 years old. Back then, the whole universe was a hot, dense plasma, a kind of glowing fog of particles and light all mixed together. As it expanded and cooled, it reached a point where atoms could form and light could finally travel freely. That light has been stretching and cooling for more than 13 billion years, and today you see it as the cosmic microwave background. The key thing here is, this is not just a pretty coloured map that scientists like to show off. When you map that glow across the entire sky, you are basically looking at a full sky scan of how smooth or bumpy the early universe was. Every little patch of slightly hotter or slightly colder radiation tells you this region had a bit more or a bit less matter than average. You're literally staring at the blueprint for every galaxy, every cluster, every large-scale structure that shows up later. So the obvious question is, how bumpy is it really? And how much freedom did the universe have to be different? The early universe was not perfectly smooth, and that tiny flaw is the only reason you exist. In the microwave background map, the hot and cold spots are not hot and cold in the way you feel temperature. They differ by about 1 part in 100,000 in relative temperature. If one patch is at some value, another is maybe 0.001% higher or lower. That is it. Those tiny shifts match tiny differences in density. Some regions had just a bit more mass, some a bit less. Gravity then takes over. Where there is slightly more matter, gravity pulls a little harder, so more matter drifts in over time. The dense spots grow denser, the empty spots get even more empty, and over billions of years the pattern grows from almost nothing into the web of galaxies you see today. But here is the problem that should bother you. If those original bumps had been weaker by even a modest factor, gravity would never have had enough structure to grab onto. The universe would have just kept expanding as a smooth, thin gas, and you would end up with almost perfect emptiness. No stars, no galaxies, no planets, no observers. On the other hand, if those bumps had been much stronger, gravity would have slammed matter together too quickly and too violently. Instead of graceful spiral galaxies with safe, stable orbits, you would get rapid collapse into huge black holes and extreme clumps, a universe full of short-lived, chaotic structures. In that kind of cosmos, long-lived stars like the Sun are unlikely, and stable planetary systems have a hard time surviving. So you are stuck between two bad outcomes: nothing ever forms, or everything collapses into monsters. Your real universe sits in a narrow band in between, where you get just enough structure to build a thin cosmic web, and a lot of empty space left over. So how sure are we that this whole story is actually correct, and not just a nice story scientists tell themselves? The answer is, the measurements of this afterglow are insanely precise. In the early 1990s, a satellite called COBE first showed that the microwave background really is a nearly perfect glow with tiny fluctuations. Then WMAP came along and mapped those temperature patterns in much more detail. Later, the Planck satellite pushed the precision even further, filling in the small-scale details with high resolution. From these maps, you can do more than just draw pretty pictures. You can read the basic properties of the universe right out of the Vita. By looking at the sizes and strengths of the hot and cold spots across the sky, you can infer how much normal matter there is, how much dark matter, how much dark energy, and what the overall geometry of space looks like. The result is that same breakdown you heard before: about 5% normal matter, about 27% dark matter, about 68% dark energy, and a universe that is flat to within a very small error, meaning its geometry on large scales is not dramatically curved. When you put that information together with other observations like galaxy surveys and supernova data, you get a very clear message. From very early times, the universe was set up so that only a small fraction of matter would condense into a web of structures, while the overall expansion, driven by dark energy, would eventually dominate and push everything apart. The emptiness later is not an accident of running out of stuff. It is built into the starting settings. The baby picture already contains the script for a universe where a few filaments light up and then everything keeps spreading into colder, thinner darkness. So what kind of universe do those numbers really describe in simple terms? They describe a cosmos that is almost perfectly smooth at the start, with just enough roughness to grow a thin network of galaxies, and no more. Not a universe overflowing with matter, where everything is close together. Not a universe where gravity instantly crushes everything into black holes. Instead, you get a universe where vast, nearly empty regions dominate. And the interesting parts, the bright structures, form a fragile skeleton stretched through that emptiness. If you were secretly hoping that once we got good data, the universe would turn out to be naturally full of life and light, the cosmic microwave background kills that hope pretty hard. That map is the baby photo that says, right from the beginning, there was never a plan for a packed, crowded cosmos. There was a plan for vast nothingness, plus a thin web of matter where complexity could briefly appear. And that sets up the next tension. If the early universe is wired for thin structure and a lot of emptiness, why does it stay that way? Why doesn't gravity, over enough time, pull more and more matter together and make things denser and more connected, instead of more isolated? To answer that, you have to look at the fight between gravity trying to pull everything together and the expansion of space trying to drag everything apart, and you're going to see that the expansion has already stacked the deck. So when you hear that the universe is expanding, what is actually moving, and how fast is this really happening? It is not galaxies shooting through space like bullets. It is space itself stretching, and galaxies are mostly just going along for the ride. The rule of thumb from observations is, for every million light-years of distance between two galaxies, their average recession speed due to expansion is around 44 miles per second. That is not a guess. That is the rough value we measure as the Hubble constant, expressed in everyday units. Now scale that up. If another galaxy is 10 million light-years away, that built-in expansion speed is hundreds of miles per second. At 100 million light-years, you're already talking thousands of miles per second. You do not feel any of this locally, because on the scale of your body, your planet, even your solar system, gravity and other forces completely overpower this gentle stretching. But over tens of millions of light years and more, the expansion wins, and it just keeps adding speed with distance. There is a critical twist here. Far enough away, the recession speed from expansion can exceed the speed of light, not because anything is breaking physics, but because it is the space in between that is growing. Light still moves at its usual speed locally, but the gap it has to cross is being stretched faster than it can cover. Those regions are not just far, they are beyond what any signal can ever reach. So you are living in a universe where distance is not just separation, it is an active process that pushes things apart faster and faster as you look farther out. So with space doing that, stretching everywhere, what chance does gravity really have to pull things together? Gravity is always attractive, always trying to pull mass closer, but it is not a magical glue. It is a force that depends on how much mass you have and how close it is. In a universe where the average density is that absurd 1 proton per cubic yard thin, gravity is working with almost nothing on large scales. On smaller scales, gravity still wins, it dominates. Inside a solar system, the pull of the sun easily crushes any effect from expansion. Planets orbit, moons orbit, and you do not see space growing between you and the Earth in any meaningful way. Inside a galaxy, the combined gravity of all its stars, gas, dust, and dark matter keeps it bound together, rotating as one system. But once you go out to the scale of galaxy clusters and beyond, the story flips, the density drops, empty space takes over, and the background expansion is no longer a tiny correction, it becomes the main effect. Clusters that are not tightly gravitationally bound to each other get carried apart by the stretching of space. They separate so fast on those scales that no amount of extra time helps gravity catch up. They become permanently isolated, each cluster stuck with its own local group of galaxies, cut off from most of the rest of the universe forever. So how do we know this is not just a nice story built from theory? How do we know the expansion, and especially the acceleration, is really happening? We look at the light from galaxies and from special types of exploding stars, and we measure exactly how that light is shifted. Light is a wave, and when a distant galaxy is receding from us because of expansion, the waves get stretched. Their wavelength gets longer, which shifts their colour toward the red end of the spectrum. This is called redshift. By measuring how redshifted a galaxy's light is and combining that with independent distance measurements, we can see how fast it is receding. Type Ia supernovae, which are a kind of exploding white dwarf star, are extremely useful here. They explode in a fairly standard way, with a predictable brightness. So if you see one that looks dimmer, you know it is farther away. These standard candles let us build a detailed relationship between how far things are and how fast they are receding. When astronomers plotted that data in the late 1990s, they expected to see a curve that showed expansion slowing down over time, because gravity should pull on everything and gradually reduce the expansion rate. Instead, they saw the opposite. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if the expansion had been slowing. The only way to make the numbers fit is to accept that the expansion of the universe is not just continuing, it is speeding up. There is some extra push built into the fabric of space which we now call dark energy, and just adding more matter to the equations cannot explain it. So what does all of this mean for the long-term future of the sky you see, and for how lonely things are going to get? The expansion does not just separate distant clusters now, it keeps going, and the acceleration makes it worse over time. There is a kind of cosmic horizon, a distance beyond which any light emitted today will never reach us, because space in between is stretching too fast. As the universe ages, more and more galaxies cross that horizon, relative to us. Their light fades, gets more redshifted, and eventually becomes undetectable. Fast forward a few 100 billion years. By then, all galaxies that are not tightly bound to the Milky Way and its local group will have slipped beyond this horizon. A future observer, living in the merged remnant of the Milky Way and its neighbour Andromeda, will look out and see only that one giant galaxy, and possibly a few small companions. No rich web of clusters, no clear pattern of expansion, no cosmic microwave background bright enough to measure. The universe, from their point of view, will look static, small and isolated. The emptiness around them will not just be large in size, it will be locked in. The evidence that the cosmos ever had other galaxies, that it ever had a Big Bang, will have been stretched away and erased from their observable patch. The expansion is not just making the universe empty, it is actively deleting the clues that it was ever anything else. And that raises the next hard question. If the expansion is pulling everything apart and isolating these regions, what does the large-scale map of the universe actually look like right now when we chart where the galaxies are and how big the gaps between them really are? When you map where galaxies actually are in 3 dimensions, you do not get a smooth mist of matter. You get something that looks like a broken spider web. Long, thin filaments of galaxies cross huge distances, clusters sit at the junctions like knots, and between them are enormous regions with almost nothing in them. These are cosmic voids. A typical large void can be 100 million light-years across or more. In regular distance units, that is roughly 600 quintillion miles of space that is, apart from a bit of thin gas and a few stray galaxies, basically empty. If you could somehow float in the middle of one of these voids, the nearest big structures would be hundreds of millions of light-years away in every direction. The universe you would feel around you would be dark and quiet, with only a few faint galaxies on the sky instead of rich clusters and dense walls of light. This is not a rare special case. Voids take up most of the volume of the universe. The web of filaments and clusters that you usually see in nice cosmology graphics occupies only a small fraction of the total space. So the next reasonable question is, if most of the universe is made of these giant low-density bubbles, what happens when you find an extreme one, a really large region that is even emptier, than it should be. One of the most famous examples is the Boötes void, often called a Great Void. It is roughly 330 million light-years across. If you stick with the same scale as before, that is nearly 2,000 quintillion miles from one side to the other. When astronomers first mapped it, they expected to see a normal mix of galaxies there, spread out but present. Instead, they found far fewer galaxies than you would predict if matter were even mildly uniform on those scales. If the Milky Way happened to sit in the centre of the Boötes void, your view of the universe would be very different. With 20th century telescopes, the kind used when we first realised other galaxies even existed, you probably would not have found many external galaxies at all. The sky would show your own galaxy, some stars, maybe a few faint smudges, and that is it. You could easily build a whole cosmology that says, this is basically all there is, and you would be completely wrong, but the data available to you would support that false picture. When scientists say the Boötes void looks like someone scooped out a chunk of the universe and did not refill it, they are not being literal, they are pointing out how different its galaxy count is from the average. It is an extreme case of an already common pattern, a hole in the large-scale map where almost nothing has collected. That leads directly to the next question. How do these voids actually form? And why does the universe invest so much of its volume in almost pure nothing, instead of more structure? Voids do not require any exotic new physics to explain them. They are the flip side of the same growth process that makes clusters and filaments. Go back to those tiny density fluctuations in the early universe that you saw in the cosmic microwave background. Some regions are a bit above average density, some are a bit below. Over time, gravity pulls matter into the overdense regions. As matter moves in, those spots get denser, their gravity gets stronger, and they pull in even more matter. But that matter has to come from somewhere, and that somewhere is the underdense regions. As gravity drains material toward the growing filaments and clusters, the low-density areas lose even more of their already sparse content. They expand and become emptier relative to the average. Over billions of years, the contrast grows. What started as a slightly underdense patch turns into a large, very empty void. The universe builds its structure by evacuating most of its volume, concentrating a modest amount of matter into a network, and leaving the rest as background emptiness. So you end up with this strange situation. The universe is not trying to fill itself in evenly. Its laws drive it toward a picture where some regions become very rich in structure, and vast regions become almost completely drained. And that leads to a deeper, more personal question. If life and advanced civilizations can form at all, how does this web and void structure affect where they can appear, and what they can see or do? Start with a simple statement. If you want lots of stars, lots of new planets, and lots of heavy elements, you want to be in the busy parts of the cosmic web, not in the voids. Filaments and clusters are where gas falls in, cools, and forms big numbers of new stars. Star formation rates are higher, the chemical enrichment is stronger, and there is simply more raw material for building complex systems. That already makes it more likely that advanced civilizations, if they exist, will show up along those filaments and near rich clusters. Now put a civilization deep inside a large void. Their local environment has fewer galaxies, fewer new stars forming, and less dense gas to work with. On the sky they would see a thin scattering of galaxies, not the rich structure we map from the Milky Way's location. They would have almost no nearby external galaxies to study. Intergalactic travel or large-scale expansion would be even more hopeless than it already is elsewhere, because the distances to any interesting targets would be larger with less to gain. In terms of resources, a void civilization would be like a town built in the middle of a desert, with a few oases very far away, while civilizations in filaments sit closer to rivers and coasts. The universe is not just mostly empty in a passive way. Through its own gravity-driven evolution, it actively sorts matter into regions that get more and more structure, and regions that get stripped out and left with almost nothing. If life depends on having enough matter and energy to build and maintain complexity, Then the universe is sorting potential life into you get lots of options zones and you get stuck in isolation forever zones. Most of the game board, most of the cosmic volume, is on the losing side of that split. You happen to live in one of the busier lanes of the cosmic web, in a galaxy with a decent star formation history, in a place where the sky is rich enough that you can even discover the web and the voids in the first place. But even in those good regions, there is a deeper twist. The visible matter that makes your galaxy is not the main thing shaping that web. The large-scale structure, including the voids themselves, is being built on a skeleton of something you cannot see directly, something that makes up most of the matter but never forms planets or people. To understand that skeleton, you have to look at the missing mass problem and the invisible halos that wrap every galaxy you know. You look at a spiral galaxy, and it feels solid, like a big spinning disk of stars that should behave under normal gravity rules. So here is the first hard question. If you take all the visible stars and gas in a galaxy, and you plug those into basic gravity, do you get the rotation you actually see? Astronomers tried that. They measured how fast stars are orbiting at different distances from the centre, and the numbers did not match. Stars far from the centre were moving way too fast. With only the gravity from the stuff you can see, those outer stars should fly off into space. The galaxy should slowly rip itself apart, but it doesn't. The galaxy stays intact. By Newton's laws, there are only two options. Either our understanding of gravity is completely wrong on those scales, or there is extra mass you cannot see, adding more gravity. When you crunch the data across many galaxies, the pattern keeps repeating. The visible matter, all the stars, all the gas you can detect, is not nearly enough to hold the system together at the measured speeds. So the simplest fix is, there is more mass there, it just does not shine. It does not emit or absorb light in any normal way. That is what we call dark matter. It is dark not because it is evil, but because telescopes that collect light do not see it. Once you accept that, the next step is to ask, how much of this hidden stuff are we actually talking about, and how is it arranged? The answer is a lot, and it is everywhere. When you model galaxies with this extra mass included, you find that the visible disk of stars is just the inner part of a much bigger structure, a dark matter halo. This halo can extend several times farther out than the visible edge of the galaxy, and it can contain maybe 10 times as much mass as all the stars and gas combined. On really large scales, when you simulate the growth of the universe with this dark matter included, something interesting happens. The dark matter clumps first, forming a rough web of dense regions and filaments. Normal matter, the atoms, then falls into that web, cools, and makes the galaxies you actually see. In that sense, the dark matter is like an invisible scaffold. No dark matter, no deep gravitational wells, no easy way for thin gas to collapse into the kinds of galaxies we see today. The bright parts of the universe are basically paint filling in the invisible shape laid down by dark matter. You might ask, is this just a clever story, or do we have direct ways to see the effect of this dark matter, other than galaxy rotation speeds? We do. One of the strongest tools is gravitational lensing. According to general relativity, mass bends space and light follows the curved paths. So if there is a massive clump between us and some distant galaxies, the light from those background galaxies gets bent, stretched, or distorted. By measuring how their shapes are warped, we can map how much mass sits in front, even if that mass is invisible. When astronomers do this around galaxy clusters, they repeatedly find that the total mass needed to cause the observed lensing is much larger than what you get from the hot gas and visible galaxies alone. The missing mass traces out big extended halos, again pointing to dark matter. Then there are special systems like the Bullet Cluster, where two clusters of galaxies have collided. In X-ray images, you can see the hot gas from the clusters smashed and slowed down in the middle. But when you map the mass through lensing, most of it has passed through and is now sitting on either side separated from the gas. That tells you the bulk of the mass is in some component that barely interacts, sliding through the collision almost untouched. Again, that lines up with what dark matter should do. Put all this together, rotation curves, lensing maps, cluster collisions, and the data keeps repeating the same message. Most of the matter that creates gravity in the universe does not shine, does not absorb, barely interacts with normal matter except through gravity. It is like a ghost that has weight. You never touch it, you never see it, but it controls the large-scale layout of everything. Now here is the part that should really get to you. Dark matter does almost nothing that you would call interesting in a human sense. It does not clump down into small, dense objects the way normal matter does. It does not form atoms. It does not make molecules. It does not host chemistry. It does not make planets. It does not build brains. It just sits there as a vast, cold mass, shaping gravitational wells, and then letting normal matter fall in and do the complex stuff. That means the majority of the universe's matter budget is in a form that is basically a background field for your story, not a participant in it. If you think of matter as the raw material for possible complexity, most of that raw material is locked in a mode that will never, on its own, create life, technology, or even solid surfaces. It just deepens the gravity pits. So the stage you live on, this thin layer of normal matter that can form stars, planets, and people, is already a minority phase. The universe chose to put almost all of its mass into something that will never directly join the interesting side of physics as you experience it day to day. That is already a cold message, but it gets worse because even this ghostly majority, the dark matter, is not the main ingredient when you step back to the largest scales. If most of the matter is dark and cannot do anything complex, what does it say about your place in the universe when you realize that the single biggest component is not matter at all, but a strange energy in empty space that is pushing everything apart faster and faster? How do you find out that the universe has quietly changed the rules on you, using exploding stars as the clue? In the late 1990s, two teams of astronomers went looking for something pretty basic. They wanted to measure how fast the expansion of the universe was slowing down over time. The logic was simple. Gravity pulls on everything, so as the universe expands, you expect that expansion to gradually decelerate. To track this, they used Type Ia supernovae, special white dwarf explosions that have almost the same peak brightness wherever they go off. Because their peak brightness is so consistent, you can treat them like standard bulbs. If you know how bright they truly are, and you see how bright they look from Earth, you can figure out how far away they are. Then, by measuring how much their light is redshifted, you can figure out how fast the universe has stretched since they went off. Put the distance and the redshift together, and you get a very clean test of the expansion history. The surprise was not small. These distant supernovae were dimmer than the slowing expansion model said they should be. Dimmer means farther away. Farther away means the universe has expanded more than expected in the time since those explosions. The only way to make the math work is to accept that the expansion has sped up. Instead of gravity gradually winning, something else started pushing, making space expand faster with time. That was not on anyone's list of normal outcomes. So the obvious next question is, what could be strong enough and spread out enough to push the entire universe apart like that? To make the supernova data fit in, and to match the detailed patterns in the cosmic microwave background, you have to add a new ingredient to your model of the cosmos, a smooth energy component that does not clump like matter, and that has a negative pressure, so it drives acceleration instead of slowing things down. We call it dark energy. When you fit all the observations together, dark energy ends up taking about 68% of the total energy budget of the universe. Here is the blunt part. We do not know what dark energy actually is. The simplest idea, and the one that currently fits the data well, is a cosmological constant, a built-in energy of empty space itself. In that picture, every cubic light-year of vacuum has some small amount of this enredo. It does not dilute as the universe expands the way normal matter and radiation do. It is just there, everywhere in every bit of volume. That gives you a very strange view of reality. The more space you have, the more of this repulsive energy you get. Empty space is not just the background. It is carrying most of the universe's energy, and it is the part that is driving the large-scale behaviour. Matter and radiation ride along on top of whatever the vacuum decides to do. So how does that actually play out over time if the density of dark energy stays roughly fixed while space keeps growing? Think of it this way. Say dark energy has a certain amount of energy per cubic light year. Early on, the universe is smaller. There are fewer cubic light years total, so the total dark energy content is modest. As the universe expands, the number of cubic light years goes up, and because the energy per unit volume stays about the same, the total dark energy increases. You're literally creating more dark energy as you create more space. That extra dark energy makes the expansion accelerate more, and that faster expansion creates more space which adds still more dark energy, and so on. It is a feedback loop. The more volume you get, the more the expansion becomes dominated by this component, and the less matter and radiation matter on the largest scales. The emptiness is not just sitting there doing nothing, it is powering the growth of more emptiness. So where does that leave the future of structure in the universe? And what does that do to your chances of ever connecting with anything beyond your local region? If dark energy keeps dominating, then over time, more and more galaxies will cross a kind of cosmic event horizon relative to you. Once a galaxy is far enough and receding fast enough, any light it emits now will never be able to fight the expansion and reach you, no matter how long you wait. It is not just very hard to get there, it is physically impossible to exchange information beyond that horizon. Clusters and galaxies that are gravitationally bound to us, like the galaxies in our local group, will stay together as a single island of matter. But everything else, all the more distant clusters and filaments, will drift away into darkness, becoming unobservable and unreachable. The universe does not only thin out, it breaks into patches that cannot talk to each other at all, as if they were separate universes with their own sealed-off skies. In that far future matter, radiation, even black holes are not the main actors. The dominant component is the energy of empty space itself. The thing steering the overall fate of the cosmos is not stars or galaxies, it is the vacuum, and that leads straight to the next pressure point. If the energy of nothing is in charge of the expansion, if dark matter builds an invisible skeleton, and if normal matter is only a small residue on top of that, then the few places that manage to stay dense and stable long enough for life to appear are not just small, they are unbelievably selective real estate. So how thin is the slice of space and time where conditions are good enough for a planet like yours to even exist, before this accelerating, mostly empty universe moves on and leaves everything else even more isolated? How big is the part of the universe where you could actually stand on a rock, breathe an atmosphere, and not instantly die? The answer is that part is shockingly small, even before you think about life. Start at the most basic requirement: liquid water. For a planet like Earth, that means a surface temperature between about 32 degrees and 212 degrees Fahrenheit, not just for a day, but for millions or billions of years. Around any given star, there is only a narrow shell where this happens, the so-called habitable zone. Put a planet much closer than Earth is to the Sun, and you risk a runaway greenhouse effect. The atmosphere traps more and more heat, oceans boil, surface water disappears. Put it much farther out and the planet freezes globally, with water locked up as ice. For a star like the Sun, this just right band is not a huge region, it is a relatively thin ring in space. Shift Earth's orbit by a meaningful amount for long enough, and you probably do not get stable oceans and a mild climate, you get a dead world. But even that picture is generous, because it quietly assumes the star in the middle is actually a good host. Most stars are not. The very massive hot blue stars look dramatic, but they burn their fuel violently and die in a few million years in supernova explosions. That is nowhere near enough time for a planet to cool, stabilize, develop complex chemistry, and slowly evolve life. On the other end, the tiny red dwarf stars are incredibly long-lived, but they flare hard and often, blasting nearby planets with bursts of high-energy radiation. That kind of constant punishment can strip atmospheres and sterilize surfaces. The best stars for complex life are in a specific middle band like our Sun, Not too massive, not too weak, stable energy output over billions of years, relatively calm compared to flare monsters. In terms of all the stars in the Milky Way, that is a small slice. Most stars are smaller red dwarfs, some are bigger short-lived stars. The fraction that looks sun-like in stability and lifespan is a minority, so now your requirements are already tight. The planet has to sit in a narrow distance band around one of the relatively rare stable stars. Then you have to place that whole system somewhere inside a galaxy, and where you put it matters. Go too close to the centre of the Milky Way and conditions get rough. The density of stars is much higher. The rate of supernovae is higher. The radiation background is stronger, and gravitational interactions are more chaotic. Orbits get disturbed more often, and catastrophic events are more likely. That is not what you want if you need billions of quiet years. Move too far out into the galactic outskirts, and you hit the opposite problem. In those regions, fewer generations of stars have lived and died, which means the gas has fewer metals in astronomy terms, things heavier than helium like carbon, oxygen, silicon, and iron. Those elements are critical for making rocky planets, complex chemistry, and living systems like yours. In the far halo you can have stars, but the raw material for Earth-like planets is scarce. When astronomers run simulations of galaxy evolution and chemical enrichment, they see a pattern. There is a ring in the disk, at certain distances from the centre, where conditions are relatively good for complex life. Enough heavy elements to build rocky planets, not too much catastrophic activity, reasonably stable environment over long times. This is the galactic habitable zone. It is not the whole galaxy. It is a band, maybe a few tens of thousands of light years wide in radius, inside a disk about 100,000 light years across. So now look at the stack. You're in one galaxy among hundreds of billions. Inside that, you're in one thin ring of better conditions, not the whole disk. Inside that ring, you need one of the minority stars that are stable and long-lived like the Sun. Around that star, you need a planet in a narrow band where liquid water can persist for billions of years. Each filter throws away most of the universe. And there is still another cut to make, this time in time, not just in space. The universe has not always been able to make Earth-like planets at all. In the early universe, right after the Big Bang, almost everything was hydrogen and helium. Heavier elements only appear after the first generations of stars live, fuse elements in their cores and explode, throwing those elements back into space. It takes several cycles of star birth and death to build up enough metals to make rocky planets in large numbers. That means there was a long initial era where life-friendly worlds were basically impossible. On the other side of the timeline, the universe will not keep making good planets forever. As time goes on, galaxies convert cold gas into stars and then blow a lot of that gas out or heat it up so it cannot cool easily. Star formation rates drop. At some point, there is much less fresh gas available to form new stars and planets. The mix of conditions you have now, enough metals, lots of reasonably stable stars forming, and plenty of gas left, is not permanent. So you get a kind of sweet spot in cosmic history. Roughly around now, plus or minus a few billion years, there are enough heavy elements around, enough calm, long-lived stars, and not yet a total shutdown of star formation. Before this window, the universe was mostly hydrogen, not yet ready to build complex rocky planets in bulk. After this window, especially far into the future, the fuel for new star systems thins out and new Earth-like worlds become rarer and rarer. Taken together, the picture is blunt. In space, you're in a tiny slice of one galaxy that has the right conditions. Around your star, you're in a narrow temperature band. In time, you're in a limited era where all the ingredients line up. Outside those slices, in almost all of space and almost all of cosmic history, planets like yours either cannot form or cannot stay stable long enough, or are sitting in environments that wreck them. You are living in the middle of a rare, temporary bloom of habitability, inside a universe that is mostly empty, mostly hostile, and already moving past its peak ability to make worlds like yours. So if your current moment is part of a short-lived peak, the next question is, what is happening to that peak right now? Are we still ramping up, or is the universe already sliding into a quieter, dimmer phase where new, stars and new chances for life keep dropping. You probably assume the universe is still in its prime, still building stars like crazy, still filling itself up with new suns and new worlds. It feels that way when you look at the Milky Way band in a dark sky. But on cosmic timescales, you are already living after the party. When astronomers add up how many new stars form per year across the observable universe, and do this at different look-back times, they see a clear curve. Starbirth ramped up, hit a peak about 10 billion years ago, and then started falling. Since that peak, the star formation rate has dropped by roughly a factor of 10. Right now, fewer new stars are turning on per unit volume than in the distant past. The universe is already less fertile than it used to be. The blue, intensely star-forming galaxies you see in deep images were more common billions of years ago than they are today. What you are watching now is the tale of a process that is slowly shutting down. So the natural next question is, what is actually turning off the star factory? Why would a universe that can make stars ever stop doing it? The basic answer is simple and brutal. Galaxies are running out of usable fuel. To make a new star, you need cold gas, mostly hydrogen, collected into dense clouds where gravity can take over and collapse those clouds. Early on, galaxies had a lot of gas relative to their mass. Over time, they kept turning that gas into stars. Every bright young blue star you see is gas converted into a compact burning ball. Once it is in a star, that gas is locked up for millions or billions of years. On top of that, the process of star formation is not gentle. Massive stars explode as supernovae, pushing on the surrounding gas, heating it, and sometimes blasting it out of the galaxy entirely. Supermassive black holes in galactic centers can launch powerful jets and winds when gas falls toward them, dumping huge amounts of energy into the surrounding region. That energy can drive gas out into intergalactic space, where it becomes too hot and spread out to easily cool and collapse again. Look at dense galaxy clusters, and you see the end stage of this. Many of the big galaxies there are quenched. They have almost no cold gas left, and they are not forming stars at any meaningful rate. They show up as smooth reddish ellipses, with older, redder stars dominating their light. The vigorous blue star-forming phase is over. They are basically coasting on their existing stellar population while slowly fading. So it's not just that gas gets used up. It is that the very processes that create stars and feed black holes also heat and eject the remaining gas. Once that gas is hot and thin, gravity has a hard time pulling it back into dense, cold clouds. That leads to the next layer of the problem: what keeps that gas hot and useless for such long periods, and how do galaxies get stripped down so thoroughly? When astronomers look at big galaxies and galaxy clusters in X-rays, they see huge halos of very hot gas surrounding them, gas heated to millions of degrees. At those temperatures, the gas glows in X-ray wavelengths, but it refuses to cool quickly enough to collapse into stars. This is where feedback comes in. Bursts of star formation and activity from central supermassive black holes repeatedly pump energy into that gas halo, stirring it, heating it, and preventing it from quietly sinking back down. In crowded clusters, there is another nasty effect. As a galaxy orbits through the hot intra-cluster medium, it is basically ploughing through a thin, fast wind of hot gas. That wind can strip cold gas out of the galaxy's disk, a process called ram pressure stripping. Picture a car driving fast with loose papers on the roof. The wind rips them off. In the same way, the galaxy's own motion through the cluster environment can tear away its remaining gas. Once that gas is gone or heated beyond easy cooling, the galaxy is effectively strangled. Star formation drops, then almost stops. So you have this feedback loop at the galactic and cluster level. Stars and the black holes heat and expel gas, the environment strips more gas away, and their hot halos prevent what is left from cooling. Over billions of years, more and more galaxies fall into this red and dead state. Which raises the next question. If you roll the cosmic clock forward far beyond human timescales, what does the sky look like when this slow shutdown is mostly complete? Push ahead tens of billions, then hundreds of billions of years. The rate of new star formation continues to fall. The big, bright, short-lived blue stars burn out quickly. What remains are longer-lived, redder stars, many of them small red dwarfs that sip their fuel slowly. The classic bright spiral patterns you see in Hubble photos become rarer. Galaxies lose their cold gas disks, merge with others, and settle into more featureless shapes. Eventually, the universe transitions from a mix dominated by active blue star-forming galaxies to one dominated by older, redder systems, filled with low-mass stars. Over even longer spans, those stars age too. Sun-like stars end up as white dwarfs, dense, cooling embers. The most massive stars leave behind neutron stars and black holes. The whole population shifts toward dim remnants. So the long-term forecast is not a glowing, eternal city of stars lighting up forever. It was never going to be that. The universe built a brief, intense skyline of star formation, peaked early, and then scheduled the lights to fade, building more remnants and fewer new suns every passing billion years. You happen to live at a time when there are still many active stars, many blue galaxies, and enough fresh gas around to make more. But this is not the default state, it is a temporary phase that is already on the decline. And that sets up a sharper version of the old question: if the universe is thinning out its supply of new stars, and if the existing ones are aging into a dimmer, quieter population, what does that do to the chances of intelligent life appearing everywhere you might hope for? And why is the night sky still so silent if the numbers once looked so promising? You've heard the question 1,000 times. If there are so many stars and so many planets, why is everything so quiet? The classic Fermi paradox assumes a generous universe, packed with opportunities. But after everything you have seen, does that picture still make sense? The real universe is not so many, it is almost none, with rare exceptions. Most of space is empty. Most stars are bad hosts. Most of the timeline is hostile to complex life. The volume that can support a technological species like you is not huge. It is a thin, patchy film in space and a short slice in time. So flip the question around. In a universe that is mostly empty, mostly dark and already past its peak for making new stars, is silence really surprising? You need the right galaxy region, the right kind of star, the right kind of planet, a stable climate for billions of years, and then a long, unbroken chain of evolution that does not get reset by impacts, flares, or nearby explosions. Every one of those filters throws away most of the possible worlds. You're not picking from trillions of easy options, you're picking from a tiny filtered subset of a subset. Even if some of those rare worlds do manage to grow intelligent life, the next problem is simple physics. How fast can anything actually move? The speed of light is about 186,000 miles per second. And as far as we know, nothing with mass can travel faster than that. In practice, any real spacecraft would go much slower. Suppose somehow a civilization builds ships that can cruise at 10% of light speed, which is already far beyond anything you can do now. At that speed, crossing the Milky Way, which is about 100,000 light years across, would still take around 1 million years. Now ask, how many things can go wrong over 1 million years of continuous high-tech expansion? Civilizations have to stay stable, avoid self-destruction, keep building and maintaining ships, handle unknown hazards, and keep caring about expansion at all. And that is just across your own galaxy. Jumping to the next large galaxy, millions of light years away, takes tens of millions of years at that same speed. On top of that, the universe's expansion is accelerating, slowly stretching the gaps between galaxy groups. Colonizing the universe is not just hard, it is almost certainly beyond what any biological or even machine civilization can realistically sustain. Even if no one tries to travel, you might think, fine, maybe they just talk, but signals have their own limits. Radio waves, lasers, whatever you use, still spread out and get weaker with distance. A beam that is bright and clear at a few light years can be faint and messy at a few thousand. Space is not silent, it is full of background noise from your own galaxy, from other galaxies, and from the cosmic microwave background. After enough distance, any signal is buried under that hiss unless you make it incredibly focused and powerful, and keep it on for a long time. Now put yourself in context. You have been loud in radio terms for maybe 100 years. That means your signal has reached a sphere about 100 light-years in radius. The Milky Way is 100,000 light-years across, so your radio bubble is 1,000th of the width of the galaxy. That is like shouting in a stadium and having your voice carry only to the first tiny ring of seats. In cosmic terms, you have not announced your presence. You have whispered briefly into your local neighborhood. So what happens if most civilizations are like that, local and brief? They light up for a few thousand or maybe a few million years, send out some signals, maybe explore or colonize a small region and then fade out. Their stars change, their planets shift, or they wipe themselves out, or they lose interest in large-scale projects. Their radio bubbles expand at light speed, weaken, and disappear into the noise. The odds that two civilizations' active periods overlap in the same region of space within detection range and at the right frequencies start to look small. Now, layer on top everything else you already know. The universe's habitable real estate is rare in space. The time window for complex life is narrow in cosmic history. Star formation is already slowing. Dark energy is pushing galaxies apart and will eventually cut off contact between large regions. Distances are huge, speed limits are strict, and signals fade. Every factor leans in the same direction, not toward a crowded universe full of chatty neighbors, but toward a universe where intelligence is rare, spread out and short-lived compared to the vast cold background. The terrifying resolution to Fermi's question might be this: nobody is visiting you not because nobody exists, but because everyone is trapped in their own small island with too little time and too much distance to bridge the gaps. Civilizations flare up in thin slices of space and time, look around their local neighborhood, wonder if anyone else is out there, and then vanish, leaving almost no trace that can cross into stellar or intergalactic scales. From your point of view, the universe looks empty. From theirs, it probably did too. So the universe is not a giant, bright city full of overlapping empires and obvious traffic. It is more like a broken chain of remote islands in a rising ocean, each one so far from the others that by the time you build enough boats, the water level has risen and the currents have changed. You live on one island, you cannot see the others, they probably never saw you. And by the time anyone learns enough physics to understand the real layout, the large-scale structure is already drifting further apart. Which leads to an even colder question. If intelligent life is local, brief, and stuck on small scales, what actually lasts in this universe? What ends up owning most of what little mass is left for unimaginably long periods of time after the brief flash of stars and civilizations is over? Right now, your sun looks calm and permanent, but some of its heavier cousins are already on a one-way path to becoming something much more extreme. When a really massive star runs out of fuel, gravity takes over in the most brutal way possible. The core collapses, the outer layers can explode as a supernova, and what's left behind can be so dense that not even light can escape. That is a black hole. The escape speed at its surface is higher than 186,000 miles per second, the speed of light itself, so once anything crosses the event horizon, it cannot get back out, no matter how much energy it has. We do not see black holes by looking for black circles on the sky. We see what they do to their surroundings. When matter falls toward a black hole, it forms a swirling disk heating up as it spirals in. That hot gas emits X-rays, so we see bright X-ray sources where visually there's nothing obvious. We see stars in tight, fast orbits around invisible points, their paths betraying a massive object with no light. And when two black holes merge, they send ripples through space itself, gravitational waves, which detectors like LIGO and Virgo have picked up. All these clues say the same thing. Black holes are real, they're common end states for massive stars, and they are already quietly collecting a share of the universe's mass. And those are just the small ones. The deeper question is, what's sitting in the centers of galaxies, shaping their evolution over billions of years? At the core of most large galaxies, including your own Milky Way, there is a supermassive black hole with a mass millions or billions of times that of the Sun. In our galaxy, the central black hole is called Sagittarius A, and it weighs in at roughly 4 million solar masses. We know it's there because we've tracked individual stars near the centre whipping around an invisible point at thousands of miles per second, on tight, fast orbits that only make sense if there's something incredibly massive and compact in the middle. In the galaxy M87, astronomers went even further. Using the Event Horizon Telescope, a network of radio telescopes spread across Earth, they produced an image of the shadow of its central black hole. What you see is a dark region where light falls in and doesn't come back out, surrounded by a glowing ring of superheated matter orbiting at near light speed. That image is not a simulation, it's data. It confirms that these supermassive objects are not just equations on paper, they're real, they're huge, and they sit at the hearts of galaxies you can point to. So if black holes sit at the end of the life cycle for massive stars, and supermassive ones anchor galaxies, what role do they play in the long-term future, when the universe has had trillions of years to evolve? Over absurdly long timescales, black holes become the main winners in the gravitational game. In a galaxy, stars orbit and occasionally have close encounters with each other, or with big masses in the centre. Some stars get flung outward, into the galaxy's outskirts, or even fully into intergalactic space. Others get nudged onto paths that take them too close to the central black hole, where they're torn apart and swallowed. Gas clouds fall in, lose energy, spiral down, and feed the central monster. Smaller black holes, the remnants of dead stars, can merge into bigger ones, gradually shifting mass into fewer, larger objects. As galaxies interact and merge, their central black holes can sink toward the middle of the merged system and eventually collide, forming an even bigger black hole. Over time, as star formation slows and existing stars age, more and more mass ends up either ejected into deep space or locked inside black holes. In the far future, the bright structured galaxies you recognize today fade, and what's left as major persistent things are these deep wells of gravity in an increasingly empty universe. That sounds like a permanent end state, but even black holes don't last forever. So what happens when the only big structures left also start to go? Quantum physics predicts that black holes slowly evaporate through a process called Hawking radiation. The details involve quantum fields near the event horizon, but the result is simple to state: black holes are not completely black. They very, very slowly leak energy and lose mass. For a black hole with a mass similar to the Sun, the timescale for this evaporation is ridiculous, a 1 followed by about 66 zeros years. For supermassive black holes with millions or billions of solar masses, it is even worse, up to a 1 followed by about 100 zeros years. During almost all of that time, there will be very little else happening. Stars will have burned out, white dwarfs will have cooled, neutron stars will be quietly sitting in the dark. The universe will be cold, dilute, and quiet. With black holes as the last concentrated reservoirs of mass energy, as they slowly emit Hawking radiation, they shrink, get hotter, and radiate faster, until eventually they evaporate completely, dumping their remaining energy into a universe that is already near absolute zero. So the final picture is not a universe filled with permanent indestructible monsters. It is a universe where even the monsters eventually fade, leaving behind only a thin bath of low-energy particles and radiation in an ever-expanding, ever-cooling space. The objects that will own most of the mass for the longest time are also temporary, which raises the final brutal step in this chain. If stars fade, galaxies thin out, black holes evaporate, and space keeps growing, what does the universe look like when there are no big structures left at all? When even the emptiness has stopped changing in any meaningful way? Right now, the only reason anything interesting exists is because the universe is uneven. Some places are hot, some are cold, some are dense, some are thin. Stars burn because there's a huge difference between the temperature in their cores and the cold of space. Planets have weather because there's a temperature difference between day and night, equator and poles. Your own body works because there's a chemical and electrical imbalance across cell membranes that can be used to drive reactions. All of this falls under one idea: entropy. Entropy is basically a count of how many ways energy and matter can be arranged. High entropy means everything is spread out and randomized. Low entropy means things are organized and concentrated. The second law of thermodynamics says that in a closed system, entropy tends to increase. In simple words, energy differences get used up, structures break down, and the overall arrangement drifts toward more mixed, more uniform, more average states. Stars, planets, and life are low-entropy exceptions, sitting on top of a general trend toward disorder. They only exist because there are still gradients to tap. As time goes on, the universe keeps using up the easy gradients. Stars take hydrogen and helium in their cores and fuse them into heavier elements, releasing energy as light and heat. That radiation spreads out in all directions, filling more and more space, getting more and more dilute. Galaxies convert cold gas into stars, and as you saw earlier, that process slows as the gas is used, heated, or blown out. Black holes collect mass into superdense clumps, but even they are not final storage. Through Hawking radiation, they very slowly convert their mass into a trickle of particles and photons that leak into space. The key point is that all of these processes move energy from concentrated forms to more spread out forms. You start with dense fuel in stars. You end with radiation spread across light years. You start with matter locked in black holes. You end with a diffuse bath of particles. Given enough time, every temperature difference, every pressure difference, every concentration gradient gets worn down. There is no law that pulls things back toward order. The one-way rule points in the direction of more entropy. If you run that forward far enough, the universe trends toward a state where the temperature is almost the same everywhere. Not exactly, but close. The background temperature sinks toward a value just above absolute zero, maybe a fraction of a degree above minus 459.67 degrees Fahrenheit. No bright stars, no hot accretion disks, no hot gas clouds, just a very cold fog of low-energy photons and very sparse mix of particles drifting in an ever-expanding space. Now ask the practical question: what can live or think in a place like that? Life and intelligence do not just need energy, they need free energy, the kind you can harness to do work. That means you need a difference: hot here, cold there, or high chemical potential on one side and low on the other. Heat engines work because there's a hot reservoir and a cold reservoir. Computers work because there's a way to move charge from one state to another and dump waste heat somewhere cooler. Brains work because there are gradients of ions and molecules that can be used to drive signals. In a true heat death scenario, those gradients disappear at the large scale. If everything is at almost the same temperature and matter is extremely dilute, there's no easy way to extract useful work. You could imagine ultra-advanced civilizations stretching out their activity, going into long sleeps, using tiny amounts of energy very efficiently, but that buys you time, not an escape. As the universe ages, the total amount of free energy available per unit volume keeps dropping. Eventually, there simply isn't enough contrast anywhere to run complex processes at all. Even if some hypothetical superintelligence somehow adapted to use the last drips of energy from decaying particles or evaporating black holes, that era also ends. When the last black hole is evaporated, when the last bound systems have decayed, and when all easy sources of energy differences have been flattened out, there's nothing left to power computation, memory, or active structure. At that point, the question who could survive stops making sense. There's nothing left to sustain. So the final state people call heat death is not just a cold universe with fewer stars, it's a universe where nothing significantly new can happen. No regions collapsing into new galaxies, no cycles of star birth and star death, no chemistry-driven complexity, just a nearly uniform sea of very low energy photons and a rare thin spread of elementary particles. Everything still technically moves, but nothing organizes itself into long-lived, large-scale structure anymore. The interesting physics is in the past. The harsh part is that this outcome is not an extra rule layered on top. It falls out of the same laws that let you exist in the first place. The same thermodynamics that lets stars shine and lets organisms extract energy from their environment also guarantees that, if you wait long enough, those sources of free energy get used up. The same general rules that created galaxies and made life possible also imply that one day, far beyond any human timescale, there will be no more galaxies forming and no more life-friendly conditions anywhere. So when people say the universe is headed toward heat death, they are not just saying it will look empty. They are saying it will be empty of possibilities, no more large-scale changes that matter, no cycles you can ride, no gradients you can exploit. The cosmos will still exist, but in a thin, frozen, almost featureless state. Which brings you to a tough, almost uncomfortable line of thought. If the end state is that empty and that simple, and if most of space and time is hostile or useless for complexity, why do you find yourself in one of the rare pockets where things are organised, full of structure, and capable of hosting minds at all? To answer that, you have to face the idea that your very existence biases what kind of universe you can see, and that emptiness, not fullness, might be the default setting of reality. You look around and see that you live on a rare, stable planet, in a calm part of a galaxy, during a brief era when stars still shine and there is plenty of usable energy. That feels lucky. The first uncomfortable step is realizing it is not just luck, it is baked into the fact that you exist at all. This is a selection effect. You can only wake up in a place and time where beings like you can exist. You are never going to open your eyes in a galaxy-free universe, because there would be no eyes. You are never going to be born in the deep heat death future, because there will be no biology left. That basic idea is called the anthropic principle. It says, the universe you see must be compatible with your existence, not because the universe cares about you, but because if it wasn't, you wouldn't be here to observe it. It sounds almost trivial, but it has teeth. It means some of the coincidences you see, like existing in a narrow habitable era in a narrow habitable zone, are not surprising once you condition on the fact that you are here asking questions. They are the only cases where observers appear at all. Then you notice something deeper. It is not just your planet and your era that look tuned. Some of the underlying numbers in physics look suspiciously just right for a universe that can have complexity. The strength of gravity, for example, controls how fast matter collapses into stars and how those stars live and die. The amount of dark energy controls how quickly the expansion accelerates. The size of the initial density fluctuations in the early universe controls how fast structure forms. If gravity was significantly stronger while everything else stayed the same, matter could collapse too quickly, making the universe more dominated by black holes and violent events, with fewer long-lived stable stars. If gravity were much weaker, clouds of gas might never collapse efficiently, leaving you with a thin mist and not many galaxies. If dark energy were larger by even a modest factor, the expansion could rip matter apart before galaxies ever form. If it were too small or negative, the universe might recollapse quickly in a big crunch before complex life has time to evolve. If the early fluctuations were much smaller, no structures grow. If they were much larger, you get a chaotic mess of rapid collapse and destruction. Tiny changes in those basic parameters can turn your kind of universe into something that is either almost completely empty or very short-lived and violent. You happen to see values that land in a narrow window where galaxies form. Stars live for billions of years, and planets can have long periods of stable conditions. That looks like fine-tuning, and it raises a blunt question. Did you just get incredibly lucky, or is there something deeper going on? One way many physicists and cosmologists try to make sense of this is by taking the idea of more universes seriously, the multiverse hypothesis. In that view, the Big Bang is not a single, isolated event that produced one universe with one set of physical constants. Instead, there is a whole ensemble of regions, domains, or pocket universes, each with possibly different values of those fundamental parameters. Some might have much stronger gravity, some much weaker. Some might have much higher dark energy, some almost none. Many of them would never form galaxies at all. Others might collapse quickly into dense, hot states with no long-lived structure. In that landscape, most universes are sterile. They're either smooth vacuums that never form stars, or they are dominated by brief, violent events with no time for complex chemistry to settle. A few rare regions happen to have numbers in the right ranges for atoms to build stars to build heavy elements, and planets to form and stay stable long enough for life. You, naturally, find yourself in one of those rare regions, not because it is typical, but because it is the only kind where anything can sit around and ask, why these numbers? That does not magically solve the problem of where the multiverse comes from, but it changes what you call special. Your universe is not necessarily singled out or designed, it is just one statistical outlier among many, and your existence filters which one you see. Here is the part that really shifts the mood. In this picture, emptiness is not the weird thing, emptiness is the default. Most possible universes are empty or nearly empty. Most possible settings of the dials give you no galaxies, no stars, no long-lived structures. Even among the tiny fraction that do allow stars and planets, most of the volume and most of the time are still hostile to life. Space is thin, habitable zones are narrow, the window for complex life is limited. So you end up here, in a cosmos that is already overwhelmingly empty and on its way to heat death. And this place counts as one of the rare good ones. You're living in a statistical outlier, in a small island of matter, during a short period when complexity is possible, surrounded not just by a universe that will eventually go dark, but maybe by a much larger multiverse that is mostly dead on arrival. That is the horror version of the anthropic argument. The universe feels indifferent and sparse because that is what reality mostly is, and you only show up in the tiny pockets where it temporarily isn't. You're not seeing a typical sample of existence, you're seeing a biased slice that is compatible with you, framed by a much larger background of nothing interesting. And there is one more twist to add on top of that. Even in this rare, slightly friendly universe, even in this brief window where you can understand any of this, the evidence you have about the true nature of the cosmos is itself temporary. The universe is not only mostly empty and short on habitable zones, it is also actively erasing the clues that would let future observers figure out what really happened. So the next step is even sharper. What does it mean if later civilizations, stuck in an even emptier, more isolated universe, will never be able to see the cosmic web, the microwave background, or the accelerating expansion that you can detect right now? How do you even do cosmology in a universe that has hidden almost all of its own past from you? Because of dark energy and accelerating expansion, the part of the universe you can see is not fixed. There is a moving boundary, a kind of horizon. Beyond that horizon, space is stretching away faster than light can ever close the gap. So any light emitted from there now will never reach you. Not in 1 trillion years, not ever. Right now you still see other galaxies, clusters, the large-scale web. But as time passes, more and more of those galaxies will cross that horizon relative to us. Their light will get stretched, red-shifted to longer wavelengths, and eventually fade out of detectability. In a few trillion years, if any observers are still around, the only galaxies they will see are the ones that are gravitationally bound to them, basically the local group that has merged into one big system, a Milky Way Andromeda remnant plus some leftovers. Everything else will be gone from their sky, not because it vanished, but because the expansion has cut off any chance for light to reach them. Now think about one of the key pieces of evidence you use today to understand the early universe, cosmic microwave background. Right now, that afterglow is already extremely cold, about 2.7 degrees above absolute zero, around minus 454.8 Fahrenheit. As the universe expands, that radiation gets stretched to longer wavelengths, its temperature falls even closer to absolute zero, and its photons get fewer and more spread out per unit volume. At some point, the CMB will be redshifted so far that its wavelength is enormous and its intensity is tiny. It gets buried under local noise, things like emission from remaining stars, gas, even instruments. No matter how good your detectors are, there will come a time when the background signal is so weak and so low energy that you simply cannot pick it out. For future physicists, there will be no clean microwave sky pattern to map, no baby picture of the universe to analyze. So picture the situation of a scientist living in that far future in a galaxy that has swallowed the rest of the local group. With no visible external galaxies and no detectable CMB, what could they reasonably conclude about the cosmos? With no distant galaxies to measure redshifts from, they would not see clear evidence of expansion. The universe would appear static on the largest observable scales. With no visible CMB, they would not have a direct signal of a hot, dense early phase. Their observable patch would look like one isolated, long-lived galaxy, maybe surrounded by some dark matter in a black, empty space. Using the data available to them, they might conclude that the universe is just that, a single island-like system in an eternal, unchanging void. Their cosmology would be wrong at a deep level, not because they are bad at science, but because the key clues have literally left their observable region. The expanding universe, the Big Bang, the web of galaxies, the detailed composition you can infer today from CMB maps, all of that information would be missing. The universe is, in a real sense, erasing its own origin story from the sky, one galaxy at a time, one red-shifted photon at a time. That means even knowledge is on a clock. Right now, in this era, you have a mix of data that is unusually rich. You can see other galaxies across billions of light years. You can measure the CMB. You can detect Type Ia supernovae in distant galaxies and read the expansion history. You have just enough structure left, and just enough of the early light still in view, to reconstruct a story of a hot beginning, a thin cosmic web, dark matter and dark energy. But that awareness is not permanent. It is tied to a specific window in cosmic time when the expansion has not yet pushed everything out of reach and the CMB has not yet faded past detectability. Go too early, and observers would not have had galaxies fully formed yet. Go too late, and they will not be able to see beyond their own gravitationally bound island. In both directions, the ability to know the true large-scale history is lost. So you are in a weird, very specific position. You live in a universe that is mostly empty, headed toward more emptiness, and on top of that, actively stripping away the evidence that would let future minds prove it. The cosmos is not just cold and thin, it is self-censoring. It shows you its large-scale structure and its origin story only during a limited phase, then locks that information away behind horizons and noise. That drops you into one last sharp question. If the universe is this empty, this temporary and this hard to understand, and if even the chance to know the truth is a short-lived privilege, what does that say about your own existence right now, as one of the rare minds that can see the pattern before it disappears? So here's the part that's hardest to swallow when you put everything together at once without looking away or softening it. On average, the universe is basically nothing. Take a random cubic yard of space and you're lucky to get a proton. Most of what exists, in terms of energy content, is dark matter and dark energy, stuff that does not make planets, does not make chemistry, does not make life. The geometry of the whole thing is expanding, then accelerating, then cutting regions off from each other so hard that light itself can't keep them connected. The timeline is not eternal stars forever. It's a brief flash of star formation and habitable conditions, followed by stretches of time that make that flash look like a rounding error, where everything fades toward cold and dark. You're not in a crowded universe with some quiet corners. You're in an empty universe with a thin web of galaxies as a side effect. The default state is near vacuum. The bright structured places you like to think of as the universe are the exception layered on top of that, and even those are temporary. Once you really accept that, the natural question is, how far out on the tail of unlikely events do you have to go for you to exist at all? Your existence needs a long chain of things to go right in sequence. First, you need a universe where the initial density bumps in the early plasma are neither too small to ever form galaxies nor too big and chaotic to avoid everything collapsing into destructive objects. That's already a narrow target. Then inside that universe, you need a galaxy that forms in a relatively calm part of the cosmic web, with enough heavy elements built up but not sitting in the worst radiation or gravitational chaos. Inside that galaxy, you need a star that is in the small, stable range, not a short-lived blue giant, not a flare-spitting red dwarf. That star has to stay reasonably steady for billions of years. Around that star, you need a planet with the right size, atmosphere and orbit to keep liquid water at the surface inside a narrow distance band where it doesn't either boil away or freeze solid long term. Then you need evolution to run, largely uninterrupted for billions of years, without a killer asteroid, nearby gamma ray burst, or runaway climate shift wiping the slate clean every time complexity starts to build. On top of that, you need a narrow technological window. Your civilization has to survive long enough to invent tools that can detect the cosmic microwave background, measure galaxy redshifts and figure out that dark energy is a thing at all. That window sits between too early, not enough data yet, and too late. All the clues have faded past the horizon. Add all of those constraints up in space and in time, and your situation is a freak coincidence stacked on another freak coincidence. So the emotional hit is not just, wow, space is big. It's space is big, mostly dead, and the stuff that's not dead is getting pushed farther apart while the tracks leading back to the beginning are being erased. The scale is too large for your instincts, the emptiness is too deep, and the future is not an open frontier, it's a long decline. If you are hoping that reality is secretly like a sci-fi galaxy map, full of overlapping empires and busy traffic lanes, the data does not support that. The more carefully we measure, the more it looks like a huge museum of absence, with a few lit rooms that eventually go dark. That can feel like a gut punch. It undercuts the fantasy that out there is automatically full of neighbours and activity. Instead, out there is mostly vacuum, mostly dark matter, mostly dark energy, with a few thin strands of matter where things briefly happen. Intelligent life, if it appears at all, is likely rare, local and short-lived, fighting with strict speed limits and evaporating free energy. The universe does not look built for civilizations, it looks built for expansion, dilution, and eventual heat death, with civilizations as side effects. So what are you supposed to do with that other than feel small? This is where you can pivot without going soft. The same facts that make the universe terrifying also make your situation incredibly sharp. If most of space is empty, if most of time is dead, and if most of possible universes never get life at all, then the existence of a mind that can even understand that sentence is extremely rare. You're not just sitting inside a random boring cosmos, you're part of a tiny set of arrangements of matter that can look up, write down numbers in light years and degrees, and see the pattern. Think about what that means in plain terms. Out of all the cubic light years of space that will ever exist, you're in one of the few that hosts a rocky planet with liquid water on the surface, orbiting a stable star, in a galaxy that still has enough structure to let you reconstruct its history. Out of all the billions of years the universe will exist, you're in a brief interval when the sky still shows you other galaxies, when the cosmic microwave background is still detectable, and when star formation has not completely faded. Out of all the ways matter could be arranged, you are part of a configuration that is running a model of the universe inside itself. That does not make the universe friendly, but it does make your moment non-trivial. In a cosmos that mostly never wakes up, consciousness is not cheap. It is not something that was guaranteed to be common. It is what happens when an unlikely chain of conditions lines up long enough for matter to start modelling the larger structure it sits in. You are right now, the universe briefly not being empty, using a brain made of atoms to notice that most atoms, most of their time, do nothing at all except drift in cold space. This is not about forcing a feel-good message on top of a bleak picture. The bleak picture is real. Average density is near zero. Most of the energy is in forms that can never host life. Expansion is isolating everything. Star formation is declining. Heat death waits at the end of a ridiculously long clock. All of that remains true. The extra piece is just this. Knowing that and being able to communicate it to someone else is itself part of the rare structure the universe almost never produces. So when you stare into the void and feel that mix of fear and fascination, that reaction is not a bug. It is exactly what you would expect from matter that has just realized how unlikely it is. You're not obligated to pretend the universe cares about you. It very clearly doesn't. But you also cannot honestly say you're insignificant in any simple way, because significance here is not about taking up space. It is about being one of the few places where the laws of physics have arranged things tightly enough that the universe can be aware of itself, even briefly. What you do with that is not a physics question. It is a practical one. You do not get to rewrite the cosmic timeline. You do not get to turn off dark energy or restart star formation. What you do get is a short window on one planet around one star where you can understand the situation and decide how you want to act inside it. Every choice you make, every piece of weird knowledge you pass on, happens inside that tiny window, under a sky that, on human scales, still looks full, even though you now know it isn't. You are, in the strictest, most literal sense, matter that figured out it lives in a desert. You are surrounded by emptiness that will win in the long run. But for the small span of time where you are here and aware, you're also the one part of the universe that is not just drifting. You can measure, you can explain, and you can choose. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.